Hi, in this video, we want to take a look at machine learning regressors. So remember, regression is when we have a supervised learning. So we have a target variable that is numeric, and we want to be able to make a prediction or make inference on with variables related to the target variable. So the predictors are our x, and the target variable is our y. And the y is a numeric variable. All right, so what we want to do today, we want to look at regression models that are not linear equations. So remember, ordinary least squares, lasso, ridge, and the Bayesian regression stuff that we've talked about before. Those all gave us linear equations for our models. Now we want to make it a little bit more exotic, more exciting, maybe new age if you want to go wild. And we're going to look at some other types of models. And these things are, a lot of people get interested in these, get excited. We're not going to talk about optimizing these models. We're not going to talk about parameter fitting. We're just going to take a real brief look at them. We're going to look at different types of models, and we're just going to run with it. All right, so once again, our data set is going to be the ultimate Halloween candy power ranking. And so we want to take a look at the percentage of times that in a head-to-head competition, the candy won against another candy. All right, and if you remember, we've got chocolate and fruity, caramel, peanutty, almondy, nougat, crisp, hard, bar, is in a box or bag, the sugar percentage, the price percentage, and then our target variable is the win percentage. All right, so then we've got values from 0 to 100 that we're going for. All right, so first thing I'm going to do, I'm going to load pandas because we need to load the data from a CSV. All right, now that we've got the data, let's go ahead and get our predictor variables going. So all the predictor variables are chocolate, fruity, caramel, peanutty, almondy, nougat, crisp, rice wafer, hard bar, is it bag or box, sugar percentage, and price percentage. And then our target variable is the percent of times that it won when going head to head with other candies. Now, what we're going to do, we're going to go ahead and we're going to do train test split again. So I'm going to break up my data into the training data, which builds the model, and the test data that we use to evaluate the model's performance. We use it to estimate how the model will perform in the future. So when I do training statistics tell me how well the data fits on the sample. Test statistics is my estimate on how well the model will fit on the population in the future. So let's go ahead and get train test split from sklearn. Let's go ahead and get mean absolute error. Now let's go ahead and split up our data. And I'm splitting my data in a 60-40 manner. And I put random state of 823. That's UCF on a telephone, by the way. And the reason why I do the random state is that if I want to repeat this later down the road and get the same results, I'll be able to. And I go ahead and shuffle in case there's anything in the data that might let like order, if order was to correlate with a variable, then it's possible that we could have some issues. All right, so first thing I want to look at is support vector machines. And it's a support vector regressor is what Python calls it. In sklearn, it's support vector regressor. And we import that from sklearn. We import svm. Let's go ahead and fit the model. Now let's do a prediction on our train set, predict on our test set. Here, we're going to get our training statistics for MAE, mean absolute error, and we're going to get the mean absolute error for our test set. Now let's take a look. What do we get? All right, so we get just under 10 for our training statistic, and we get just above 11 for our test statistic. All right, well, it's saying that our model on average would be about 11% off. Is 11% good? Is it bad? Well, honestly, it depends on your problem. If that's acceptable, we could go with it. If there's not much of a penalty for being wrong, 11% is okay. But also, it's a question of what other options do we have? If I have a better model, of course, I would use that model instead. All right, so now let's go ahead and look at stochastic gradient descent. And here, we're pulling stochastic gradient descent regressor in. So it's SGD regressor. And now let's go ahead and fit the model. I'm making my predictions. Now let's go ahead and get our training and test statistics. Let's see what we get. All right, so here on training is 7.6, and it's just below 10 for the test set. All right. You know what I want to do? I want to mix it up. I'm going to change it to, I'm going to change some values. Let's see if we can improve this just a little bit. So let's see what happens. And it's about the same. All right, so something that's very important, and you'll learn this when you get into data mining 1, is you need to go through and find the optimal parameters for your model, for your data. And so what you'll do is more than likely you'll do like a grid search. You'll select different values to try for each parameter, and you try all combinations out, and then you pick the one that's the best. And that is how you determine the parameters for your model. Well, what you'll do that for every single type of model you want. You go through, you find the best parameters you can find for all the different types of model structures, and then among all of those, so here you've actually potentially made hundreds of models, you'll take the best one. Now let's take a look at K nearest neighbor. So we're going to pull in K neighbors regressor. Let's see. All right, so here I'm just going to put number of neighbors is 2. That's not very big. And our algorithm is the ball tree algorithm. I think that's a fun name, so I put it in there. All right, so now let's go ahead and get our predictions. Let's get our mean average error. Now let's take a look. All right, well, wow, look at that training. Look at that. We have, that's a big jump on, or big drop on our training, right? So that's looking good. That's making me feel good. But then I look at my test set and I go, huh, it's slightly worse than the other ones. The training statistic looked really good, but then when I got to the test statistic, I'm like, oh, well, that's disappointing. All right, so that's something we have to watch out for. This is a good example of why we want to do the train test split. Because if I didn't do train test split, if I used my entire data set to build the model and I use that same data to evaluate model quality, I would have felt like this was a really good model. And I would have been like, really pumped up and excited. But you know what would happen? I would have gotten smacked in the face down the road. And I would not have expected it. All right, well, let's try another one. Let's go ahead and let's see if we can improve this. Let's change that up to 5 for the number of neighbors. All right, now it's back to, it's similar to what we had before, 7.2. Let's take a look at the test, and 10.2. All right, I mean, that's not great, it's not better than what we had before, but I'm less concerned about being overfit on this model because these are closer together. All right, now let's go ahead and look at Gaussian process regressor. I'm going to call it GPR. Now let's go ahead and fit it. Let's go ahead and make our predictions. Now let's get our MAE. And let's look at our statistics. So wow, look at that. Look at the training statistic. It's so exciting. I mean, it's less than 0.2. On the training data, it's less than 0.1%. It's teeny tiny on the training data. But look what's going on the test data. It's 53.2. All right, just let you know, if you just made the prediction of 50 every single time, you know what? You have actually had a better model. Yeah, it doesn't make sense. And if we would have instead used the sample average, it would have been even better than that. So what has happened is that this model is clearly overfitted. This is a bad model. This is a crap model. You absolutely would not want to use this under any circumstance. But there's a but coming. What's going on? This might be a good model structure, but I have bad parameters. So if I was interested in using Gaussian process regressor, I would have to go through and try a whole bunch of different values for the parameters at what we call grid search until I found the best one. A lot of times when you get this super tuning aspect that you get here, what can happen is if you take the time to fit the model right, you can get a stellar model. But you have to worry. The more flexible and more fitting the model is, the more likely you are, or the more risk you have of overfitting the model. So you have to be very careful about this. In this situation, I would, because this is a small data set, if I was to go through and attempt to make the best model possible, I would want to do cross-validation a lot of times to make sure that I'm not going to get smacked in the face down the road. All right, let's go ahead and take a look at decision tree. So remember, a decision tree is the building block for other models. We usually don't use decision trees themselves. They usually don't fit very well. They are a part of other models like random forest and gradient boosting. All right, let's go ahead and fit the model. Let's go ahead and make our predictions. Oh, and you'll notice here, whenever I see the output from the fit, it tells me what the parameters are. What we will do is, for our model, we'll go through and change these up and we'll go through a whole bunch of different combinations of different values to get the best model possible. All right, so now let's go ahead and get our mean absolute error. Let's take a look. Wow, less than 0.2. Oh, so it's it fits the training data really, really well. What do you think is going to happen on the test set? 13.8. I mean, that's not, compared to the 53, that's not bad, but that is not our best test statistic yet. Here, this is pretty close to our best training statistic, but remember, I don't care about the training statistic. I only care about the test statistic. All I do is I use training and test I use the training to make sure that it's in the ballpark of the test. And if there's a big discrepancy, I'm worried about being overfitted. All right, now let's use gradient boosting. All right, gradient boosting, what this does is that this takes a look at the error. So it builds a tree, looks at the errors, and then builds a tree to correct the errors. Then it reevaluates the errors, builds a tree to correct those errors. Then it looks at the errors again, the new errors, and then builds a new tree to address those errors, and it keeps on doing this. This is what's called boosting. Let's go ahead and get gradient boosting regressor. Let's fit it, and then let's go ahead and get our predictions. Let's get our mean absolute errors, and let's take a look. All right, 7 and a little bit over 2. Not too shabby. All right, now let's look at a neural network with multi-layer perceptron. All right, multi-layer perceptron was like at one point like the sexy, very highly used neural network. It's kind of dropped out of favor since then, but it's still a good way to go. It's not a bad choice. So let's go ahead and take a look at it. If you want to learn about neural networks, this is a good place to start. So we want our MLP regressor. Let's go ahead and fit the model. Let's get our predictions. Let's go ahead and get our error statistics, our mean absolute error. So let's take a look. It's 27 on my training set. That sucks. That's not good. Let's do our test set. It's about the same. It's actually a little bit better. All right, so some things about this. Multi-layer perceptron, you know, the more like hidden nodes and hidden layers that I have, the better it's going to fit. And it can overfit on a model really, really well. Here, if I was to go through and get the right parameters and take my time with this and work on it for a while, I could probably get the best. This could probably be the best model out of all the ones that we've looked at if I want to put in that effort. So what we're going to do in real life is we're going to go through, we're going to select a bunch of different model structures like we did today. And then we're going to go through and we're going to try and find the best parameters for each of those structures. After I do that, I find the best overall model and I run with that. All right, that's all I've got for you for now. Stay safe and take care.